Hi students. So today we begin lecture 77 in our aerospace engineering course, and today I'm going to talk about the jet engine. So essentially the jet is something which is nowadays used in most of the aircraft, whether they are passenger aircraft, fighter aircraft and so on. And in this video we are also going to discuss about the turbojet, the turbofan, the turboprop and the ramjet. So at the end of this video you will know how the jet engine works and how to calculate the thrust for a typical jet engine. This is lecture 77. I am Dr. Ranjan Ganguly. So if we look at the typical aircraft which are flying around nowadays, you will see that there are a plethora of jet aircraft. And when we see a typical transport such as a Boeing or an Airbus in which we are flying around, we will see that the engine is something like this. So you will not see propellers in most cases. Instead, you will see what is known as a jet engine. So what happens in the jet engine is that the air comes in from the front, there is some combustion which takes place inside and some more processes, and then the air is thrown out from the exit. Similarly, if you see most of the current military aircraft, you will see that they are powered by jets. For example, in the case of this aircraft here, you can see there is a jet engine here. So there will be an intake here, the air will come in, there will be combustion taking place and so on, and then the air will be exhausted out of this exhaust here. So this is the basic premise of the jet engine. Of course, there is a lot of complexity inside this particular device here. This is a very expensive piece of equipment. It can cost a lot of money, and the entire industry which is devoted to jet engines and so on is in the realm of billions of dollars. So that's something which makes it very important for aerospace engineering applications. Now, if we think about the basic concept of how the propeller works versus how the jet works, we will see that what the jet does is that it takes a small mass of air and gives it a large velocity change. Whereas what the propeller does is that it takes a large mass of air and gives it a small velocity change. Now, whatever be the mechanism, what is happening at the end of the day is that the momentum of the air is changing. So, remember, momentum is mass into velocity. That's something we know from basic physics. And Newton's second law essentially says that force is equal to the rate of change of momentum. So that's the actual representation of the Newton's second law. Most of the time we take m out of the bracket in many mechanics classes and so on, but we don't need to do so. And that's the equation we are going to use today for all our work. Now, if you want to look at the concept of the jet engine, we'll see the concept is actually very simple. There is an inlet and there is an exit. At the inlet, you have velocity coming in. This velocity is V infinity. At the outlet or the exit, you have the velocity V subscript E. Now, what happens is that inside the jet engine, some kind of combustion takes place, and so energy is imparted into this system, and at the end of this particular process what happens is that the exhaust velocity is typically much higher than the intake velocity. So that's one of the things which typically happens in jet engines, is that VE is much greater than V infinity. So that's something we know intuitively when we think about a jet engine. So that's actually the bedrock of some of the theories which we are going to look at today. Now we are going to spend some time in developing a math model which is going to give us the equation for thrust for the jet engine. So that's of course the practical use of the jet. We want to generate a thrust out of this particular device. Now if we look at the jet conceptually, we'll see that there are two broad pressures which act on the jet. One is inside the engine itself. This pressure is P subscript S, and outside the jet the pressure is P subscript infinity, that is the ambient pressure. So it's the differential of this pressure and the components of this pressure in the x direction which is going to contribute to the particular thrust we see. One more thing to remember is that the inlet cross section is A subscript I and the outlet cross section is A subscript E. So if we look at it from front, we may see something like this, that there is a region here in the blue which has area given by AI minus AE. Now, if we are planning to calculate jet thrust, we will see that the thrust will be composed of two parts. One is the part due to PS. So what we can do is we can take all the components of PS and we can sum them along the wall and take the component in the x direction. So that's this first integral here. The second term is going to be all the components of P infinity. We again take them on the wall and then we sum them in the x direction. So essentially thrust will comprise of two parts. One is because of PS and one is because of P infinity. Now in this case we are neglecting all the shear stresses here. We are assuming that the pressure, the normal pressure is much more than the shear stress here. Now, therefore, we can write this equation, and of course, now what we need to do is we need to simplify it. We need to find out some estimate for these quantities. So, as far as the quantity involving P infinity ds is concerned, you can simplify it easily because P infinity is a constant. You can bring it out of the integral, and then this dsx simply becomes ai minus ae, which is this cross section in blue which I have shown here. So the P infinity term is relatively simple, but the problem happens that the PS ds x component is rather difficult to estimate. So that's something we are going to spend some time trying to estimate, and then we are going to return to this particular equation which I have put here in yellow. Now to get the estimate of that PS part of the problem, what we are going to do is we are going to look at the control volume of the gas. And now we know that the gas also exerts pressure on the duct. So the gas is going to act in this manner. There is going to be this pressure system PS acting on it. And the duct is going to exert equal and opposite pressure PS on the gas in the control volume. So this is how the figure is going to look like, at least on these two surfaces here of the control volume. Now if we look at the front and the back surfaces of the control volume, in the front the pressure is going to be P infinity, and at the rear end the pressure is P subscript E at the exhaust. So from this particular pressure distribution we can say that the force which acts in the x direction on the control volume of the gas is going to be P infinity into AI, that's the force in this direction, plus the PS ds component in the x direction, which is given by this integral, minus the PEAE component because PE is acting in the reverse direction. So there is a negative sign there. So this particular equation in yellow is something which is coming out of the control volume type of thinking. Now we can get a similar expression by considering the momentum change in the complete system. So if you look at the momentum change at the exit, you have m dot air plus m dot fuel into VE. That's the momentum. So that's the one which is at the exit, and you have to subtract it from whatever enters the system. That is m dot air into V infinity. So this force in the x direction would also equal this particular quantity which I have put in this yellow box. Now, of course, I can take these two terms and I can equate them because they are essentially the same thing. They are the forces in the x direction. And if I equate these two components, I get this particular equation here in blue. Now, here you can see that the fundamental aim of getting this equation was to get this particular integral here. So what I can do, I can rewrite this equation. I can bring this integral to the left hand side, and on the right hand side I have these two momentum terms, and I also have plus PEAE minus P infinity AI. So I have moved these two terms here, and so I get this important equation in yellow. So now this has given me the equation for PSDS component X integral, which I can go back and use in the thrust equation. So this is the equation for this integral. Now of course we had already derived the equation for thrust here, and now we can take this particular integral and we can substitute it into the thrust equation. So we do that. First we expand this thrust equation out in this form here, and then we rewrite it after substituting this PSDS term here. Now when we do that we get this equation. Now what happens is that a couple of terms cancel out. So the terms which involve AI, they are going to cancel out. So there is a minus P infinity AI here, there is a plus P infinity AI. So after that cancellation, I am only left with terms involving a subscript E, that is the cross section at the exit, and I am left with this remaining terms which involve the momentum change in the gas. So the thrust is the momentum change which takes place in the airflow or the gas, and there is also a pressure component which is there, which involves the differential of pressure between the exhaust and the input side, and this is multiplied by the AE or the exit cross section. Now, of course, if we want to be very fastidious, we should use this equation for T, and that's something we can do in a real system. But if we want to get a good picture out of the thing in terms of concepts, we could use a fact that m dot fuel by m dot air is very small quantity. It is about 5%. So we can neglect m dot fuel into this equation. So if we neglect m dot fuel here, we can drop this term, and so we get a reduced expression as far as T is concerned. So this is a more amenable expression for thrust, and you can clearly see here that this component is going to play a big role, and it's clearly telling you that VE should be much greater than V infinity if you want to generate a lot of thrust as far as the jet engine is concerned. So this is again the fundamental thing we started out with, and now we can see it coming out of the equation. Now just to go back in history, the jet fighters, or rather I should say the jet engine, came up quite late. So there was a long period where propellers were popular from the time the Wright brothers took off to about 1944 when the Germans came up with the first jet fighter, the Me-262. So if you are interested in that aircraft, we can go in Google and search about it. Now, as I mentioned before, most of the modern fighters, of course, use jet engines. Now, let's look at the first type of jet engine, which is, I would say, the most fundamental or basic or classical jet engine, and that is the turbojet. So if we look at the turbojet for typical subsonic conditions, we have a system like this. So essentially, we have the components diffuser, we have compressor, we have burner, turbine, and nozzle. So these are the main components of the turbojet. Now what happens is that the air will come in, it will slow down in this whole region, that is the diffuser and compressor. It gets compressed, it gets burnt in this particular region called the burner or combustor, and then it is exhausted out through this nozzle, and also it goes through this turbine. Now essentially this first part is the compression process, and the last part here from 4 to 6 is the expansion process. And what happens is that the compressor consists of certain mechanisms known as rotors and stators. These are essentially blades, and similarly the turbine consists of rotors. Now one thing which is very important to remember is the nomenclature we use here. So we use 1 here at the inlet, we use 2 to 3 the compressor region, we use 3 to 4 as the burner region, 4 to 5 as the turbine region, and 5 to 6 as the nozzle region. Of course, the velocity at the input is V infinity and at the exit is VE. So let's look at each of these devices, or rather the subcomponents of the jet engine, and what they do. So diffuser, of course, decelerates the incoming air from the inlet, and then it throws it into the compressor. Now if you are dealing with a subsonic type of situation, this is going to be a duct shaped like this. If you are in supersonic, the duct shape may be different. That's not something we will consider in this class. Maybe you can look at it in some later classes. Now the compressor is going to compress this air, and it consists of a series of rotating and stationary blades. Now the rotating blades are typically known as the stators, or rather the rotors, and the stationary blade as the stators. Now the geometry and manufacturing of this particular system is very complex, and it involves a lot of intricate numerical machining. Now the next part is the combustor, and here what is done is that fuel is injected in the airstream and burnt at constant pressure. So that's what I'm showing here through these fire symbols which tell you that burning is taking place here. Now then you go through the turbine, which is this region here 4 to 5, and this is where the hot gases flow through the turbine, and turbine actually drives the compressor. So turbine is producing power which drives the compressor, and some of this power is also sent into the different things which the aircraft requires to do. So whenever you are flying in any aircraft and you are expending power in some way, maybe you are charging your laptop or watching a movie, this power is typically coming through the turbine. Now the flow here is an expansion process. We are going to see that in detail in the PV diagram. Finally, we have the nozzle, and the flow is going to expand through the nozzle further, and it is exhausted out of the engine with the velocity V subscript E, or the V exit velocity. So now we can look at the PV diagram, or the pressure volume diagram of the ideal turbojet. So what would happen is that from 1 to 2 in the diffuser, you essentially go through compression, 2 to 3 you go through more compression in the compressor, and at this point you then go into the burner and you go through this constant pressure combustion or burning. Now from 4 to 5 in the turbine and 5 to 6 in the nozzle, you go through these expansion periods, and then you have essentially completed this round from 1 to 6. Now these curves here which I have given in green and purple, they essentially show isentropic processes. So remember that these are frictionless processes, as well as they are processes which have no heat transfer taking place. And then here of course you have the constant pressure part of the burning taking place. So that's essentially the ideal turbojet diagram which you need to keep in mind. Now what happens is that there is a derivative of the turbojet which in fact is more popular as far as commercial aircraft are concerned, and this is known as the turbofan. So in the turbofan what happens is that the turbine drives a fan also here. So in addition to the compressor, the turbine also drives a fan, and what the fan does is that it splits the air coming in into two parts. Some of the air is sent through the typical jet engine, and the remaining air is then sent through the shroud here. So what the turbofan is trying to do is to kind of combine some of the aspects which are positive for the propeller with what is positive for the jet. So it is trying to increase the mass of air which is being sent through the particular system here. Now if you look at this picture, it will probably become more clearer. You see that you have a large ducted fan in front, and so this fan is rotating. Then there are compressors, burner, turbine, and so on. And of course you will see that this particular large ducted fan is being run by the turbine here. This is something which is quite ubiquitous as far as modern transports are concerned, modern passenger jets are concerned. Now, like I mentioned, for the turbofan, the turbine drives both the fan and the compressor. The ducted fan is able to accelerate a larger mass of air, and so it turns out that the turbofan engine is more efficient than the turbojet. It consumes less fuel and less money, and that's something which is very important for commercial jets, because as you know, the airline industry works on very thin profit margins, so any profit you can make is certainly very welcome. So the turbofan thrust can be said to be the sum of the fan thrust and the jet thrust, which is the total thrust which is generated by these two systems, or accelerating these two masses of air. Now, one more derivative of this turbofan concept, if you extend it further, is the turboprop. And in that case, what happens is that you no longer have a shroud, instead, you have a pretty big propeller. And this propeller is something which is then also acting just like a typical propeller. It is accelerating a relatively large mass of air and throwing it backward here. Now, in most turboprops, what happens is that 85% of the power is generated by this propeller, and the turbine in this case drives both the propeller and the compressor. So in contrast to the typical piston or reciprocating type of engine which we discussed before, which is used in much of the smaller airplanes which use propeller, what happens is that turboprops are used in some of the larger aircraft, and they have a lot of advantage in terms of the advantages which accrue to the propeller, such as they can take off and land at runways which are relatively smaller in length. They may be cheaper, and also certain low speed conditions they may be more optimal than jets. Now, at the other extreme, there is the concept of the ramjet. And in the ramjet, what you try to do is you try to get rid of all that expensive rotating machinery which is present there in the compressor and turbine. Now, one of the things about compressor and turbine design is that these are very sophisticated and difficult processes, because lot of intricate machining is involved, lot of high end materials are involved, and so on. Particularly the turbine has to function at very high temperatures, and therefore the turbine design is not only a problem in terms of mechanical engineering but also in terms of material science and so on. So one of the things which people try to do, especially if they are trying to power something like a rocket or something which only has to go on a one-way mission, is that they get rid of the rotating machinery, and a device which can do that is the ramjet engine. So ramjet is shown here. Again, it will take some air and throw it out at higher velocity, but it doesn't have a compressor and turbine. Instead, the air simply goes in through a diffuser. That is a combustion zone here where combustion takes place, and then it is exhausted out of the nozzle. So in this case, the points here are simply 1, 2, 3, 4, and all that complex and expensive rotating machinery which is present in the compressor and the turbine has now been discarded. So obviously the cost of the ramjet is going to be much lower than the turbojet or the turbofan. Now, of course, there are several negatives as far as the ramjet is concerned. One of those is that even to start or operate a ramjet, you have to be moving. So you need to have some velocity coming in at a reasonable speed. And therefore, ramjets are typically launched from something, maybe a rocket, maybe a catapult, maybe an aircraft itself. And the subsonic efficiency of the ramjet is going to be very low. So these are some of the negative aspects of the ramjet. Now, if we look at the PV diagram of the ramjet, we see something like this. So essentially what happens that if you go 1 to 2 region in the diffuser, you are essentially going through this region where you have compression, then you have constant pressure burning, and then you have the expansion phase here in the exhaust nozzle. So this is a very simple system. 1 to 2 here is the diffuser, 2 to 3 is the burner or the combustion zone, and 3 to 4 is the exhaust nozzle, after which you basically throw out the gas air mixture, petrol mixture or fuel mixture out of this system here. Now, of course, these two curves here are what are known as isentropic curves. They correspond to PV gamma is constant and PV gamma is one more constant here. Now, these of course again mean that you are assuming frictionless and adiabatic flow conditions. So, to summarize today's rather complex lecture, we can say that jet engines are now pretty much the workhorse as far as aerospace engineering is concerned, especially because people want to fly from point A to point B at a relative high speed. So, you not only see most of the commercial jets are using the jet type of engines, but you also see that many smaller aircraft such as business jets have become quite popular. So in all these cases, you are using this basic equation here. You are trying to take the air, you are trying to perform some combustion, and you are trying to exit the air at a higher velocity. So the key fact in the jet engine is that you want to achieve a exit velocity which is substantially greater than the velocity of air which is coming in. Now we of course discussed the derivatives of the turbojet such as the turbofan and the turboprop, where what you try to do is you try to accelerate a larger mass of air, and so in many cases that type of system becomes very efficient. Now, like I mentioned, efficiency is a very important parameter because the airlines and various passenger transports want the aircraft to be as efficient as possible because prices of fuel are very high and they are a substantial part of the airline industry. We also discussed the case of a ramjet. Now, a ramjet can be used to power various vehicles which want to go from point to A to point B but may not seek to return. So, if you are somebody who is interested in a one way mission, then the ramjet may be something to go for. In many cases, also, if you do not have the knowledge of complex systems such as compressors or turbines, ramjet is something which you can think about. Now, one of the things I didn't mention about the ramjet is that at very high velocities, it is somewhat more efficient and it can be actually used in many such conditions. So, if you are talking of supersonic and further, ramjets may be the way to go. So that was the lecture for today about jets, about turbojet, turbofan, turboprop, and ramjet. And we saw that these all are essentially governed by PV diagrams which involve isentropic processes and also involve constant pressure combustion. I will end this video now. I think the next lectures are going to be about rockets, and till now what we have considered is known as air breathing propulsion. So essentially you can see whether it's a propeller, whether it's a jet, these are breathing in air and then they are doing some combustion and throwing it out. So in some way they are somewhat like biological systems. Like we breathe in, we do combustion and throw the air out. They are also trying to do the same thing. But in the next lectures, I'm going to consider rockets. And one of the things rockets need to do is that they need to be able to work in situations where there is no air, like in space. So in that kind of case, you should be able to generate your own way in which you can do combustion. You do not have access to oxygen, for example, in those cases. So I'll end my video now and I will see you in my next lecture. See you then.